My name is Dr. Andrew Sanchez, PhD in Chemical Engineering. In this video, we're going to go over basic examples for Lewis structures. So whether you're just starting off in AP chemistry, high school, or college chemistry, or you want to review for organic chemistry, this video is for you. If you stick to the end of this video, I guarantee you're going to feel a lot more confident drawing out the Lewis structures from scratch. Okay, so what are Lewis structures? They're just 2D diagrams that show how valence electrons are arranged around atoms in a molecular ion. Okay, and so they're going to help us understand how atoms are bonded, where lone pairs are located, and whether or not we have double or triple bonds, and finally, as well as the formal charge. Okay, so make sure you're really comfortable with formal charges and valence electrons. But if you're not comfortable, let's review that now. The number one tip I'm going to have for you for this section is the periodic table is your bestie. The periodic table is your best friend for all of chemistry, including general chemistry and organic chemistry. Let's break this down. How many valence electrons does hydrogen have? Okay, so hydrogen is going to live in the first column of the periodic table. So let's highlight this first column. So here we are in column 1, and so this is column number 1. So all of these elements right over here are going to have one valence electron. Remember, a valence electron is going to be the number of electrons in the outermost shell, and hydrogen is our first basic element. It's only going to have one valence electron. Okay, so we're going to draw H like this with a dot right there. So that's our one valence electron. Lithium, same thing. So it lives in the first column, so it's only going to have one valence electron. We're going to draw a dot right over there as well. Same thing for sodium. So sodium lives right over here. It is going to be Na with a single dot. So all of these elements that live in the first column are only going to have one dot. What about the second column here? The second column is going to be two valence electrons. I'm going to denote that with Ve. And so, for example, beryllium, which lives right over here, is going to have two valence electrons. I'm going to draw a Be, and then I'm going to draw a dot right over here, and then I'll draw a dot on the other side like so. Same for magnesium. Magnesium is going to have a dot up here and down over here. Okay, so first column, one valence electron. Second column, two valence electrons. Now, you might think for columns 3 through 12, we're going to continue that. We're going to ignore the transition metals. Why? Because there's tons of exceptions in general chemistry. General chemistry is all about learning these rules and then never following those rules again. So what we're going to do is go all the way to the right-hand side of the periodic table and look at these elements that live right over here. Do you know the name of these elements? Okay, these are going to be the noble gases. So the noble gases are going to have a complete octet. So what is an octet? Great question. I'm glad you asked. So an octet, comes from the word oct as in octagon. So it's going to mean 8 electrons. But again, we have some exceptions. So helium is an exception. So helium is only going to have 2 valence electrons, just like magnesium. Okay, but it still has a complete octet. Another word for complete octet means these are happy. They are happy. Okay, so even though helium only has 2 valence electrons, it still has a complete octet. It is happy. It is satisfied. Neon has a complete octet. So neon is going to have, well, 8 electrons. The way we draw these 8 electrons is like this. We're going to draw one on top, one on the bottom, one on the side, and one on the side. Do not double them up until we fill these 4 like this. Then we can double up the one on top. That's going to be number 5, 6, 7, and 8. Okay? If I'm going too fast for you, let me know if I should do a follow-up video on valence electrons. Now neon has a complete octet because, again, it lives in this column. What about argon? Complete octet. So I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8. Again, notice that I'm drawing them from top to bottom, side to side, and then filling those in top to bottom, side to side. Okay, so all of these elements have a complete octet. Okay, so let's go ahead and put a number 8 up on top here for 8 valence electrons. Now we're going to go 1 to the side, and from every point on here, we're going to subtract by 1 and get a total of 1 less valence electron. So these right over here, these are called the halogens. okay, they're going to have 7 valence electrons, okay? So for example, fluorine is 1 less than 8, so that's 7. So we're going to draw an F with a total of 1, 2, 3, 4, 5, 6, 7, okay? So that is fluorine with 7 valence electrons. Chlorine is also a halogen. So all of these again have 7 valence electrons. Chlorine is going to be 1, 2, 3, 4, 5, 6, 7. Make sure you don't do it the way I did. Let's redraw that one more time. Let's go top to bottom, side to side. 3, 4, 5, 6, 7. Okay, so now we're going to have 7 valence electrons here. Whether or not our last electron that lives by itself is on the side or down here, not a big deal as long as we have a total of 7 valence electrons. What about for these elements over here? So these are going to have a total of 6. Okay, 6 valence electrons. So oxygen is going to be right over here, is going to have a total of 1, 2, 3, 4, 5, 6. Okay, and then we're going to keep subtracting 1. 6 minus 1 is 5. 5 minus 1 is 4, and then 4 minus 1 is 3. So for example, nitrogen is going to have a total of 5, 1, 2, 3, 4, 5. Again, it doesn't matter if you place that second one here, here, or here, as long as we have a total of 5, with 3 of these are single. And then lastly, carbon here. So make sure that each of these are single by themselves. Do not double up the electrons with carbon. We need a total of 4. And then lastly, boron is going to have 1, 2, 3. Okay, so again, that's the trick here. We go all the way to the 8, 7, 6, 5, 4, 3. Okay, so this is really, really important that you understand the number of valence electrons before even starting Lewis structures. So how to draw Lewis structures. So here we have a step-by-step list, so you never feel overwhelmed about how to draw Lewis structures. Okay, my suggestion is do not memorize this list. Okay, we're gonna go through this list right now, but do not memorize this list. Okay, rather I want you to do practice problems. Okay, let's write that down. So don't memorize this. Okay, so don't memorize, practice instead. That being said, let's go through this list and see how we count the Lewis structures. So first things first, we're going to count all the valence electrons from all the atoms involved. That's why we went over valence electrons, because it's the first thing. Second step is to choose the central atom. Usually is going to be the least electronegative. Keyword is usually, so again, there's going to be tons of exceptions in this list here. Okay, then we're going to count the outer atoms to the central atom. Then we're going to count the outer atoms to the central atom using only single bonds. Okay, then we want complete octets. Every element has to have a complete octet, except for our exceptions. Then we're going to place any remaining electrons on the central atom. If needed, we're going to form double or triple bonds, okay, if we need to move things around. And then we're going to confirm the total electrons that we match from step 1. Okay, and then last but not least, we need to count the formal charges. And don't worry, we're going to go through all of these steps one by one. Again, do not memorize, practice instead. Hey everyone, thanks so much for watching this video so far. I do want to let you know that I am offering private tutoring for various STEM subjects at various difficulties, ranging from high school to college level STEM. This includes anything from math, chemistry, and physics. So whether you're in algebra, trigonometry, pre-calculus, or calculus, or even AP chemistry, general chemistry, or organic chemistry, or physics, I got you covered. You can sign up for a free consultation call at the link in the description, or go to engineeringminds.co for more information. Now back to the video. Okay, now that we reviewed the valence electrons and the step-by-step process, we're going to go ahead and draw the Lewis structures for the following compounds. We're going to start slow with our H2 molecule. I'm going to go ahead and bring up our periodic table just in case, but before looking, see if you can remember where H lives on the periodic table and how many valence electrons it has. Okay, very good. So H lives right over here. So remember, we said that's the first column. It's going to have 1 valence electron. So we're going to have 1 valence electron for H. Okay, and then let me move this to give us a little more space. And this as well. Okay, so we have 1 valence electron for H. So I'm going to go ahead and draw our H like this here, okay, with 1 valence electron over here. And then might as well just draw a second H with another valence electron like this. Now what we're going to do is we're going to bring these closer together, okay, just like this, and I'm going to go ahead and just move my electron right over here to create a pair just like this. Let's just kind of move it around. And very good. So this is basically our Lewis structure. Now, for every pair of electrons, we're going to erase that and form what? What do you think is going to form right here? Okay, now that I had a pair, I erased that and I turned that into a single bond. So for every pair of electrons, a single bond formed. Okay, let's write this down. Single bond formed. Okay, and so our single bond formed, that is our Lewis structure for H2. There's not much we can do about that, okay? Now I want you to try the same idea for oxygen here. So how many valence electrons does oxygen have? Let's just put 1 O right here, okay? And we're going to go to the periodic table. Remember, we said we have 6 right over here. Why? Because I said we have 8, then 7, and then 6, all right? So we're going to go ahead and draw 1, 2, 3, 4, 5, 6 for our one oxygen, but we have to bond it to another oxygen. So let's go ahead and draw our valence electrons like this. 1, 2, 3, 4, 5, 6. Okay, perfect. So all we got to do now is bring these closer together. Okay, all we got to do now is bring these closer together. Okay, so now we have our 6 electrons on each oxygen. Once again, we do have a bond right here that is formed. So let's go ahead and erase this and create a single bond like that. So now let's count how many electrons each oxygen has. Remember, we want to have a complete octet. As a matter of fact, let me erase that before we make that bond here. Let's count how many electrons this oxygen has. 1, 2, 3, 4, 5, 6, 7. Okay, so this is a problem. This has 7 electrons. We need to have a total of 8 electrons, but it only has 7. Okay. What about this one on the right? Also has 1, 2, 3, 4, 5, 6, 7. This is also a problem. What are we going to do? We basically got to just move this oxygen slightly like this. I notice I have this electron right over here. Electrons do not like to be by themselves. This one also by itself. So here's what I'm going to do. I'm just going to drag this, okay, and just like that, move it like that, okay? Okay, just like that. Now, this is bad practice. I do not want you to drag because more than likely you're on paper. So what we're going to do instead is in our brain, I'm just going to go ahead and redo that. And since you're probably using paper, I'm going to go ahead and just draw what would we get here. So we'd have these 2 electrons right over here. And then we're going to redraw our 2 electrons from the top and bottom. So that way we don't have to worry about dragging. I just want you to see that. Okay, very good. Now we have these 2 lone pairs. Now that we have these 2 lone pairs, we're actually not going to form a single bond. We're going to form a double bond. So for every 2 electrons, we have 1 bond. So that's basically like if we draw a line from here to here. So that's called a double bond. And the last thing we have to do is just for best practices, we're just going to arrange our electrons just so it's a little bit more symmetrical. So for oxygen, they typically are going to be on the side at an angle kind of like this, okay? Not a big deal, but we just want to do the chemistry way. And perfect. Now let's count our total number of valence electrons. Remember, our double bond is going to be 2 each, so these are shared, okay? So this oxygen on the left is going to have a total of 1, 2, 3, 4, 5, 6, 7, 8. That's fantastic because our octet is complete. And then on the right, we're going to have 1, 2, 3, 4, 5, 6, 7, 8. And this is also complete. So that is our Lewis structure for O2. All right, great. Another really important molecule we have to do is H2O. Super, super important molecule for H2O. Let's go ahead and notate our H, which we said was 1 valence electron. We're going to have another H right over here. Okay, and then another oxygen, which again we said has 6. 1, 2, 3, 4, 5, 6 valence electrons on the oxygen. Okay, and so what we're going to do here is basically rearrange our H's. 1 is going to go over here, and then 1 is going to go over here. so we can create some bonds. Again, it's not good practice to rearrange them like that, and since I know you're probably using pen and paper, let's just go ahead and redraw it manually. I'm going to go ahead and take my oxygen, and what I'm going to do is basically curve my H's a little bit down. Why am I doing that? Because now we have some bonds right over here, and I'm effectively moving my lone pair to be up on top right over here. Okay, that's because oxygen is highly electronegative. What does electronegative mean? It means that, okay, let's write that down. It's highly electronegative. Electronegative. So this oxygen is highly electronegative. That means it actually wants electrons. So that means it's like a magnet drawing some electrons. It's pulling them from the H, okay, and creating a slight separation. So now the H's are a little bit farther from the electrons than they originally were, okay? This is going to cause polarity here, so really important concept. We're going to represent that with a little bit of minus right over here on the oxygen, okay? And if the oxygen molecule is going to be a little bit closer, okay, then we're going to represent this with the following symbol here. We're going to write this squiggly D here. This is called a delta, okay? And so this squiggly D indicates a partial charge, okay? Which means, again, our oxygen is highly electronegative, which means it's drawing our electrons like this, kind of like a magnet. So let me just draw a magnet real quick, right next to this oxygen molecule. Okay, and if I color these H's here in red, then this is going to be like a magnet, whereby the south pole is up on top and the north pole is down over here. That's effectively what we have with our partial charges, and so therefore I'm going to draw a partial positive on the magnet side here on the bottom of the H's here to indicate, again, polarity. So this is called a polar molecule. Okay, so polarity happens when we have a highly electronegative atom that is drawing electrons more than another atom. The last thing we have to do is just erase our lone pairs, create a single bond just like that. Okay, and that is going to be our Lewis structure for water. Okay, I know this can be a little bit complicated, but water is super important for you to understand. Okay, and we're going to see this over and over again. All right, so that's going to be our Lewis structure for water is going to be CO2. Okay, the next one is we're going to do is going to be CO2. So for CO2, we have to guess which one is the center atom. Okay, for CO2, we're going to guess which one is the center atom. Do you think it's going to be carbon or oxygen? Okay, well, we're going to just guess. So because we have carbon on the side here, I'm going to just guess that's going to be our center atom. Okay, so I'm just going to guess that carbon is my center atom. Why did I guess that? Because, well, I just know. But you might be asking, how do you know what's the center atom? Well, you can just guess and check. So maybe you don't know. I'm just going to guess and place my carbon right here, my oxygens to the side just like that. Okay, perfect. So now we have a skeleton. We need to fill this in with the rest of the valence electrons. Okay, so I'm going to do a carbon atom right over here, which has a total of 1, 2, 3, 4 valence electrons. How did I know this one has 4? Because again, the periodic table, we have 8, 7, 6, 5, 4. So again, carbon has 4 valence electrons. Okay, then my oxygen is going to have a total of 6. So I'm going to draw 1, 2, 3, 4, 5, 6. Okay, and then 1, 2, 3, 4, 5, 6. Okay, then how do you think we're going to bond these together? Okay, basically going to move this oxygen right over here just like that. Okay, and then move this oxygen closer like here just like that. Very good. So now hopefully you can see that we are going to form a bond right here and right here. But there is a problem. We have a lone electron right over here and a lone electron over here. So we can't have lone electrons. They need to be in pairs. So I'm going to scoot this one back and scoot this one back. Okay, and effectively I'm going to drag my electron over here and over here just like that. But again, what I'm going to do is just kind of start over, so that way we can see exactly what's going on. My oxygen is going to be, our lone pair is now moved over here. And so effectively, I'm going to pair this electron with this electron and move those together here. Okay, so I'm going to erase this one and bring it right over here. And effectively, we're going to erase this one, and I'm going to effectively bond this electron with this electron right over here. So I'm going to erase this one, okay, and then create a double bond like so. Okay, so now we have a double bond on the left hand side and a double bond on the right hand side. Okay, and again, the last thing I'm going to do is just move these electrons on our oxygen, which again I told you is better convention to have our diagonal like this. Okay, so that's going to be our Lewis structure for CO2. Let's just go ahead and double check that our octet is complete. Remember, a double bond represents 4 electrons on each side, so we have a total of 8 on the carbon. We are good here. On the oxygen side, we have 1, 2, 3, 4, 5, 6, 7, 8. We're good right here. And then on oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8 right over here. And we are good. Perfect. So the next one we're going to do is going to be NH3. So NH3 is going to be a total of, okay, a total of N right over here in the center. Okay, and let's see how many valence electrons it has. Okay, it's going to be a total of 5 valence electrons. Okay, so it's going to be a total of 1, 2, 3, 4, 5. We also are going to have H on the sides, but I know right off the bat that I'm going to have our H with 1 molecule right over here and 1 electron over here. So that's pretty much all we're done here. Hopefully this is getting a little bit easier. We're just going to erase those and create a single bond here. Okay, notice that nitrogen has a lone pair, but in total, if you were to count these 1, 2, 3, 4, 5, 6, 7, 8, that is a total of 8 electrons. Hydrogen only has 2, but 2 is fine for H, and so that is our Lewis structure for NH3 ammonia. Alright everyone, thanks so much for watching this video. I do hope this was helpful. If you have any questions, feel free to drop a comment down below. In the description, there's a ton of goodies for you. You can download the notes for this practice series with the solutions. I also have a free Discord community where you can join in the link in the description. If you're looking for a community where you can ask questions, interact with other STEM majors, or just overall have a good time doing STEM problems, go ahead and tap the link in the description to join the free Discord. Once again, my name is Dr. Andrew, PhD in Chemical Engineering. I do have private tutoring available for various STEM subjects. So if you're getting confused, if you're feeling lost with subjects like chemistry, physics, mathematics, definitely sign up for a free consultation at the link in the description, or go to engineeringminds.co for more information. Again, I can help you out with various STEM subjects, whether you're in high school or college, ranging from topics such as algebra, trigonometry, calculus, general chemistry, organic chemistry, physics, and engineering. Thanks so much for watching, and I'll see you in the next video.